Welcome to Next Generation. Visual, a stunning, abstract visualization of a neural network firing. Glowing lines of data flow like synapses, forming complex patterns. The camera pulls back to reveal this network is powering a self-driving car navigating a futuristic city. Narrator. Every major technological leap of our time, from you, the AI that can write an essay or create a masterpiece of art, to the complex simulations that predict climate change, to the very cars that will one day drive themselves, runs on a single specialized type of computer chip. This chip is the engine of the 21st century. It's the most sought-after piece of silicon on the planet, turning the company that makes it into a titan worth over $1 trillion. Visual, quick cut to a grainy, 90s-style image of a booth at a Denny's diner. The contrast is jarring. Sound effect, record scratch. Modern music cuts abruptly. Narrator. But what if I told you this world-changing technology wasn't born in a pristine Silicon Valley lab with government funding? What if I told you it all started right here, in a Denny's over coffee and grand slams, with 3 friends who just wanted to make video games look better? Visual, a shot of an early, pixelated 3D video game from the 90s. The graphics are blocky and crude. Narrator. What if I told you that the company behind this revolution was just 30 days from total bankruptcy, forced to bet its entire future on a single roll of the dice? And what if I told you the secret to their $1 trillion empire was a massive, decade-long gamble on a software platform that, for years, almost no one used? Visual, flash forward to a massive, modern data center. Rows of servers hum with power, each featuring a glowing Nvidia logo. The music swells back in, epic and powerful. Narrator. This is the story of a company that saw the future 30 years before it arrived. A company that built the engine for a revolution that nobody else even knew was coming. We will uncover the brutal business decisions, the near-fatal mistakes, and the one core belief that allowed them to transform from a niche gaming company into the foundational pillar of artificial intelligence. By the end of this video, you will understand how Nvidia didn't just predict the future. They built the tools that made it possible. This is their story. Music shifts to a more narrative 90s-era synth track. Visual, an AI-generated image of a young Jensen Huang, Chris Malachowski, and Curtis Preem sitting in the Denny's booth, sketching ideas on a napkin. Narrator. Our story begins in 1993. The world was on the cusp of a revolution. The personal computer was no longer just a tool for spreadsheets and word processing. It was becoming an entertainment device. And the holy grail of that entertainment was 3D graphics. The ability to create immersive, three-dimensional worlds was the next great frontier. In a Denny's in San Jose, California, 3 engineers saw this frontier and decided to conquer it. Jensen Huang, a brilliant director from LSI Logic, and 2 talented engineers from Sun Microsystems, Chris Malachowski and Curtis Preem. Visual, show a timeline of the early 90s tech scene. Images of companies like Silicon Graphics, 3DFX, and ATI. Narrator. They founded their company with a vision to become the leader in a new type of computing, graphics-based or visual computing. They named it Nvidia, a play on the Latin word invidia, meaning envy. But the landscape they were entering was a brutal graveyard for startups. The graphics chip market was already crowded with dozens of companies, each fighting to the death for a piece of the pie. To survive, you had to be smart, fast, and willing to take enormous risks. Entertainment element. A graphic showing a Pac-Man-like Nvidia logo gobbling up smaller logos of defunct 90s graphics companies. Sound effect. Classic arcade, waka waka sounds. Narrator. Their first big idea was to build a chip that could do everything. Graphics, sound, and general processing, all in one. It was called the NV1. They even secured a major deal to use it in the Sega Saturn console's PC port. But the NV1 was a classic case of trying to do too much. It was based on a complex technology called quadratic texture mapping, while the rest of the industry, led by Microsoft's new DirectX API, was rapidly moving toward a simpler standard: triangle-based polygons. The NV1 was a commercial failure. The Sega deal collapsed. By 1996, Nvidia was on life support. They had burned through most of their initial funding and were just months away from shutting down. Visual: a diagram showing the complex NV1 architecture, which then gets a big red X stamped over it. Show a graph of the company's cash reserves plummeting toward zero. Narrator: this was Jensen Huang's first defining moment as a CEO. He made the gut-wrenching decision to abandon their first product, lay off nearly half the company, and pour every last dollar they had left into a single, desperate bet: a new chip, codenamed the Rive 128. This time, they would not try to reinvent the wheel. They would embrace the industry standard of triangle-based polygons and focus on doing one thing better than anyone else. Speed. Visual: a cinematic shot of a single poker chip being pushed to the center of a table with the Nvidia logo on it. The text, "All In," appears on the screen. Narrator: the Riva 128 was a Hail Mary pass. They had enough money to fund the company for about 30 more days. If the chip failed, Nvidia was finished. The engineering team worked with a frantic intensity. They knew the stakes. When the first prototypes arrived, they were a revelation. The Rive 128 was a monster. It was dramatically faster than anything from competitors like 3DFX or ATI. It offered high-end performance at a mainstream price. It was the product that would save the company. In its first 4 months on the market, they sold over 1 million units. Nvidia was back from the dead. Visual: a fast-paced montage. Engineers cheering in a lab as the first benchmark results for the Rive 128 come in, the chip flying off store shelves. The company's revenue graph shoots up from the floor. Narrator: the success of the Rive 128 taught Jensen Huang a crucial lesson that would define Nvidia for decades. It's better to create a market than to fight over an existing one. While their competitors were building separate chips for 2D and 3D graphics, Nvidia integrated both onto a single piece of silicon. This made PCs cheaper and more powerful, accelerating the adoption of 3D gaming for the masses. But this was just the beginning. Jensen had a much bigger vision. He didn't just want to make graphics chips. He wanted to invent a new kind of processor altogether. Visual: a blueprint of a simple CPU, central processing unit, is shown. Next to it, a much more complex multi-cored blueprint begins to form. This is the GPU. Narrator: in 1999, Nvidia coined the term that would change computing forever: the GPU, or Graphics Processing Unit. With the release of the GeForce 256, they declared it the world's first GPU. This wasn't just marketing hype. It was a fundamental reimagining of what a graphics chip could be. A CPU is designed for serial processing, doing one complex task at a time very quickly. A GPU, on the other hand, is designed for parallel processing. It has thousands of smaller, simpler cores that can do thousands of tasks all at once. Think of it like this. A CPU is a single genius chef who can cook a complex gourmet meal by himself. A GPU is an entire kitchen staffed with 1,000-line cooks, all chopping vegetables simultaneously. For graphics, which involves calculating the color and position of millions of pixels at the same time, the parallel approach of the GPU was a massive breakthrough. Visual: a clear, simple animation comparing a single-lane highway, CPU, with a 1,000-lane superhighway, GPU, both moving data. Narrator: the GeForce GPU cemented Nvidia's dominance. They had outmaneuvered and out-innovated their rivals. The graphics wars of the 90s were over, and Nvidia was the undisputed champion. They were on top of the gaming world. But inside the company, a secret, far more ambitious plan was already taking shape. A plan to unleash the power of the GPU beyond just making games look pretty. A plan that would be incredibly expensive, take over a decade to mature, and for a very long time would look like a colossal mistake. Narrator: By the early 2000s, Nvidia was the king of the hill. Their GeForce line of GPUs was the gold standard for PC gaming. Each new generation was a major event, pushing the boundaries of realism and visual fidelity. They had a thriving, profitable business, and could have easily rested on their laurels, content to dominate the gaming market for years to come. But Jensen Huang saw a different future. He saw the thousands of parallel processors on his GPUs as a form of untapped supercomputing power, and he became obsessed with the idea of unlocking it for general-purpose use. Visual, a montage of stunning video game graphics from the early 2000s, showcasing Nvidia's prowess. Games like Doom 3 and Half-Life 2. The graphics become progressively more realistic. Narrator. The first step was a feature called the programmable shader. In the past, graphics effects like reflections or shadows were fixed function, hardwired directly into the chip. Programmable shaders allowed game developers to write their own custom code, or shaders, to create unique visual effects. This gave artists incredible creative freedom. But it also did something else, something far more important. It opened a back door. For the first time, people outside of Nvidia could program the GPU to do things it was never originally designed for. Visual. An animation showing a fixed pipeline in a chip. Then show a new programmable door opening up, allowing developers to insert their own code. Narrator. Almost immediately, a small community of scientists and academic researchers saw the potential. They realized that the massive parallel power of a GPU could be used to accelerate complex scientific simulations. They started hacking the graphics card drivers, using the language of programmable shaders to perform calculations for things like molecular modeling, financial analysis, and weather prediction. It was clunky and difficult, but the results were astonishing. A single, consumer-grade Nvidia graphics card could perform certain tasks faster than a multi-million-dollar supercomputer. Visual, a split screen. On one side, a massive, room-sized supercomputer from the early 2000s. On the other, a simple desktop PC with a glowing GeForce card inside. An arrow shows the PC is outperforming the supercomputer on a specific task. Entertainment element. Text on screen. Supercomputer power. For the price of a PlayStation. With a satisfying sound effect. Narrator. Jensen Huang saw this tiny emerging trend and made another bet-the-company decision. But this one was different. This wasn't a short-term bet on a single chip to save the company. This was a long-term, multi-billion-dollar bet on creating an entirely new market from scratch. He tasked his best engineers with building a full-fledged software platform that would make programming GPUs easy and accessible for everyone. A platform that would turn every Nvidia GPU into a fully programmable parallel computer. They called it CUDA, Compute Unified Device Architecture. Visual. The CUDA logo appears on screen. An animation shows it acting as a bridge, connecting the GPU hardware to a world of different applications. Science, finance, AI, etc. Narrator. The development of CUDA, which launched in 2006, was a colossal undertaking. It cost hundreds of millions of dollars every year. It required a fundamental shift in the company's identity, from a hardware company to a hardware and software company. Wall Street hated it. Investors complained that Jensen was wasting money on R&D for a market that didn't exist. Why were they pouring resources into a scientific computing platform when their main business was selling to gamers? Many, inside and outside the company, thought it was a huge, expensive folly. Visual. A graph showing Nvidia's R&D spending increasing dramatically, while their stock price remains flat or dips. Show headlines from financial news questioning the strategy. Narrator. But Jensen was playing the long game. He famously told his team, "If we build it, they will come." He made CUDA free to download. He invested heavily in universities, training a new generation of students and researchers to program on his platform. He was building an ecosystem, a community of developers who would find new and amazing uses for his hardware. For years, the adoption was slow. It was mainly used in niche scientific fields. But Nvidia was patient. With every new generation of GeForce card they sold to gamers, they were also secretly shipping a potential supercomputer. They were building a massive, globally distributed network of parallel processors, waiting for the one killer application that would need it. Visual. A world map slowly being populated by millions of tiny, glowing dots, each representing a CUDA-enabled GPU being sold to a gamer, unknowingly becoming part of a global computing platform. Narrator. That killer application was bubbling up in a field of computer science that had been around for decades, but was long considered a dead end. Artificial intelligence. Specifically, a subfield called deep learning, which used neural networks inspired by the human brain. The problem was that training these neural networks required an astronomical amount of computation. Training a model to, say, recognize a cat in a photo could take weeks or even months on a traditional CPU. The field was stuck. Visual, an animation of a neural network, looking slow and struggling to process data on a CPU. The process is painfully slow. Narrator. Then, in 2012, everything changed. A team of researchers from the University of Toronto, led by Alex Krzyzewski, decided to enter the annual ImageNet competition, the Olympics of computer vision. Their task was to train an AI model to recognize objects in millions of different images. Instead of using CPUs, they did something radical. They used two consumer-grade Nvidia GeForce GTX 580 GPUs. They used CUDA to train their deep neural network, AlexNet. The results were breathtaking. Visual, a cinematic shot of a computer screen showing the AlexNet code running. The progress bar is moving incredibly fast. The results of the ImageNet competition are displayed, with AlexNet's accuracy score shattering all previous records. Narrator. AlexNet didn't just win the competition, it annihilated it. Its accuracy was so much higher than the runner-up that it stunned the entire AI community. It was the Big Bang moment for modern AI, and it was made possible by the massive parallel processing power of Nvidia's gaming GPUs. The secret weapon that Jensen Huang had been building for nearly a decade had finally been discovered. The AI revolution had begun, and Nvidia was about to hand out all the picks and shovels for the gold rush. The victory of AlexNet at the 2012 ImageNet competition was the shot heard around the world for the tech industry. It was definitive proof that deep learning worked and that Nvidia GPUs were the key to unlocking its power. Suddenly, every major tech company, every university research lab, and every AI startup on the planet had the same urgent need. They needed GPUs. And not just a few, they needed thousands. Tens of thousands. Visual, a rapid-fire montage. Sundar Pichai of Google, Mark Zuckerberg of Meta, Satya Nadella of Microsoft, all on stage talking about AI-first strategies. Behind them, images of massive data centers being built. Narrator. The market that Jensen Huang had been patiently building for a decade exploded into existence overnight. Nvidia was in the perfect position. They weren't just the best option. For a long time, they were the only option. Their CUDA platform, which they had poured billions into, was now their most powerful weapon. It was a deep, protective moat around their hardware business. Researchers had spent years writing code and building models on CUDA. Switching to a competitor's chip would mean rewriting everything. The ecosystem Jensen had so carefully cultivated had now locked in the entire AI industry. Visual, an animation of a fortress with the Nvidia logo. A wide moat labeled CUDA surrounds it, preventing competitors from reaching the castle. Narrator. The demand was astronomical. Nvidia's data center business, once a tiny fraction of their revenue, skyrocketed. Their stock price, which had languished for years, began a historic climb, turning Nvidia into one of the most valuable companies in the world. They were no longer just a gaming company. They were the foundational infrastructure provider for the artificial intelligence revolution. They had successfully executed one of the most audacious and far-sighted business pivots in corporate history. Visual, a graph showing Nvidia's stock price from 2012 to the present day. The line goes nearly vertical, rocketing past established tech giants. Entertainment element. The stock chart line turns into a rocket ship, launching into the clouds with a whoosh sound effect. Narrator. But Nvidia didn't stop there. They doubled down. They started designing chips specifically for AI, introducing tensor cores, specialized hardware within their GPUs designed to accelerate the specific mathematical operations used in deep learning. They built their own AI supercomputers, called DGX systems, selling them as a data center in a box to companies that wanted to get started with AI immediately. They created a complete end-to-end platform, from the individual chip, to the server, to the networking, to the entire software stack. They made it easy for their customers to buy more and more from them. Visual. An exploded view of a DGX server showing the individual GPUs, the networking components, and the software layers, all with the Nvidia brand. Narrator. This complete ecosystem approach allowed them to expand into new frontiers. They saw the potential for AI in the automotive industry and created Nvidia Drive, a platform for self-driving cars. They envisioned the next evolution of the Internet, the metaverse, and built Nvidia Omniverse, a collaborative platform for creating virtual worlds and digital twins. In each case, the strategy was the same. Use their dominance in hardware and the CUDA software platform to become the essential tool for developers in the next big technological wave. Visual. A montage showing these new frontiers. A sleek, self-driving car navigating traffic with an Nvidia interface. Architects collaborating in the Omniverse to design a building in real time. Narrator. When the generative AI boom hit in the early 2020s, with the public release of models like ChatGPT and Midjourney, it was like pouring gasoline on an already raging fire. These new large language models were even more computationally hungry than their predecessors. Training a model like GPT-4 required tens of thousands of Nvidia's most advanced GPUs, running for months. Nvidia had the only chips on the market capable of handling the task at scale. They had a near monopoly on the engine of generative AI. Jensen Huang, the man who started his company in a Denny's, was now universally recognized as a visionary, the quiet architect of the modern AI era. Visual. A powerful image of Jensen Huang on stage at a keynote wearing his signature leather jacket, with a massive screen behind him showing the latest AI breakthroughs. Narrator. The journey of Nvidia is a masterclass in long-term vision and conviction. The first lesson, solve a hard problem. They didn't chase easy markets. They focused on the incredibly complex challenge of parallel computing, knowing that if they could solve it, immense value would be unlocked. Second, build a platform, not just a product. The hardware, the GPU, was brilliant, but the software, CUDA, was what created a loyal, locked-in ecosystem and a durable competitive advantage. Visual. The two key takeaways are shown as text on screen with iconic visuals. 1. A complex mathematical problem being solved. 2. The CUDA logo connecting to hundreds of other application logos. Narrator. And the final, most important lesson. Have the courage to invest in a future only you can see. For a decade, Nvidia poured billions of dollars into CUDA and their data center ambitions, enduring skepticism from Wall Street and the press. They were building the infrastructure for a world that didn't exist yet. They understood that you can't just wait for the future to happen. You have to build the tools that will enable it. From making pixels in a video game move faster, to powering the very fabric of modern artificial intelligence, Nvidia's story isn't just about building a successful company. It's about having a vision, weathering the storms of doubt, and ultimately, building the engine that will drive the next generation of human progress. Final visual. The camera starts on a close-up of a single, complex Nvidia GPU. It pulls back to show it in a server, which pulls back to reveal a massive data center. The data center then transforms into an abstract representation of a global AI network, glowing and pulsing with intelligence, before resolving into the clean, simple Nvidia logo on a black screen.